Ruther's Guts Videos returns to your screen with another enthralling episode of the dynamic programming, in this case edit to distance, a close relative of the LCS or longest common subsequence problem. This is sort of the diff algorithm, those of you who know the diff program. So our exercise here is to convert one string, such as them, into another string using a series of edits. And the edit operations we're allowed to perform are insertion, deletion, and substitution. This can work on sequences of any particular object of any type. In this case, I'm going to assume sequences of characters, strings in other words, but it could be sequences of words or sequences of lines or sequences of anything really. So how would you convert them into Tim? Obviously you would use the T directly. Then you have a choice. Do you delete the H? Do you insert an I? Do you change the H to an I? And there's all sorts of options. You may want to play with them a bit, but it's relatively easy to convert them into Tim in a minimal number of operations. Obviously you wish to preserve the T and the M. We'll see that done in a few minutes. Here's another example, trying to convert A, which is the string A, which is GACTGC, into this catchy tune ATCTCCG. These are obviously genetic codes of some sort, and there's a particular solution, one of several, that you may want to look through. It says, well, we'll delete the G, we'll copy the A down, we'll insert a T, copy the C down, copy the T down, change the G to a C, copy the C, and insert a G. You may want to look through that, see what other sequences of operations you can come up with. You can see it takes a deletion, insertion, substitution, and another insertion. With this particular solution, that's an edit distance of 4. I'm going to assume through the rest of this video that the costs of insertion, deletion, and substitution are all just 1 unit. They don't have to be equal, but it does make the programming and the implementation a little bit easier. Okay, let's move on. Here's a sort of solution along the lines of the LCS approach. We're going to use recursion, surprise, surprise, and we're going to deal with substrings of A and B. Here's a substring of A which goes from A1 up to AI, so it's of length I, and another substring for B which goes from B1 up to BJ, so that's the length of the substring of B is J. As with LCS, we're going to first of all look at the last characters in our two substrings. Does AI equal BJ? Are the two characters equal? If so, then we can simply, the zero cost of matching them, the edit distance, the cost of converting one string to another, is clearly now just the cost of that group there. That is the D or edit distance up to I-1 and J-1. If they're not equal, then we're going to have to edit in some way, and the three options we have are deletion, insertion, and substitution, and here they are drawn out for you. So if we delete the character AI, then we're going to have to recurse on this. The B hasn't been changed, we haven't deleted anything from that, but we've taken one less character, we have one less character of the A substring. So there's the group we recurse on, that is the D I-1J recursion. The other two, insertion, we recurse on I and J-1, so we leave A unchanged, but we've got one less character in B to deal with. Or we substitute, we replace the AI with the BJ. Think it through, see if you can understand all that lot. Here it is, written out in a more recursive recurrence relationship form. So there's 3 base cases. Actually there's only 2, but I kind of like to pull one of them out just to make the discussion go a bit easier. Remember, these are one origin strings, so I and J are the string lengths in Python. So if we have empty strings, both I and J are 0, we've got 2 empty strings, what does it cost to convert one into the other? Obviously nothing. That's a 0 cost. 0 edit distance if you prefer. So alternatively, if the first string is of non-zero length I, but the second string is of 0 length, then we have to convert, for example, we have to convert a string blah into a string empty. And what's the cost of that? It's 4 deletions. So we have to delete all I elements of A. The other way, when we have to get from the empty string to some other string like blah, then clearly we have to insert characters. In this case we have to insert 4 of them. That's the J there. So those are the base cases. As I say, the first one's kind of redundant. It's subsumed by those two, but and you won't program it in specifically, but it's easy to think about. If you've satisfied the base, or if you haven't satisfied the base case, then you have to look at the recurrence that's available to you. In other words, you have to recurse. So first of all, we check the end characters, the AI and BJ. These are the cases here. They're drawn out again for you here. If AI equals BJ, then we're going to recurse on the 2 substrings reduced in size by 1. There it is there, I minus 1, J minus 1. Otherwise, we're going to have to find which works best, deletion, insertion, or substitution. We do a recursion on the 3 different options that you were seeing in that slide there. The DI J minus 1, DI minus 1, J minus 1. There's 3 in there. I missed one of them. I minus 1 J, I J minus 1, I minus 1, J minus 1. And then you have to add 1 because whatever cost you got in the recursion, you've had to do a deletion, insertion, and substitution to get there. That costs you 1 for all of them. There's the code that does it. I'm not going to go through it. It doesn't exactly make exciting video watching. You should be able to look through it. You should be able to understand it and relate that back to this here. It's just an implementation of it. At this point, it's not top-down DP. It's simply a recursive implementation, which will work for smaller strings, not for long ones. If you want longer strings, you'll have to add caching. I leave that to you as an exercise. It then becomes top-down DP. Here's a graph showing the recursion for the strings we had before, the them into Tim problem. The last characters match, so we can delete them and we get the and t remaining. And in order to get to this new node, we did an alignment operation, an A. I often call it copy or transfer. It's a 0 cost, hence the 0 there. The last characters of THE and TI do not match, so we have to use one of the recursions, and these are going to have a cost of 1 in each case. So a deletion, D1, a substitution, S1 means cost of 1, I, and is an insertion with the cost of 1. As I say, they could be different costs. I'm not going to worry about that now. You can worry about that during the quiz. And so on. I'm not going to go through all of this. I would, however, like you to compare it with the LCS version, where we looked at the longest common substring, which of course was of length 2, and we had a very similar looking graph, except that there were only 2 arcs out of each of these internal nodes. Here there are 3 because we have the substitution option as well. All that remains is to turn this into a bottom-up dynamic programming problem or solution. How do we do that? Well, surprise, surprise, we build a table. And I just happen to have one handy here. Here's our DP table. It goes from 0 up to 3, where 3 is the length of the string Tim, 0 up to 4, which is the length of the string them. The noughts here mean empty substrings. So this case, or this top corner, is the first of the base cases I drew out for you there. That's when I equals j equals 0. What does it cost to convert the empty string into the empty string? It costs 0. What does it cost to convert the empty string into T or TI or TIM? It's 1, 2, and 3 respectively. Notice these are not zeros as they were in the LCS case. So this is the insertion costs here. If I'm going from them, or T, TH, THE, or THEM to the empty string, then I have to delete characters. So I have to have a 1, 2, 3, and 4 costs there. And those are the 3 base cases you're seeing there. Like I say, the top one is really part of the other 2. The rest of the table has to be filled out using the recurrence relationship. That's the last 2 lines. And we first of all always have to check whether the AI equals the BJ. For convenience, I've put the strings here and there. So this is BI, this is AI down here, this is BJ up here. So we can simply compare the characters at the edge of the row and the head of the column. So does T equal T? Yes, it does. That's this case here. So we simply copy the cost diagonally into here. If, as in this case here, they don't match, so T does not match I, so we look for the cheapest of the 3 neighbors and we add 1 to it. Cheapest neighbor is of course the 0 that we just put there, so we put a 1 in that box. Same again, t does not match m. Cheapest of the three neighbours is the 1. We're going to add 1 to it and get a 2. Now I'm going to briefly fill out the next couple of lines in the table. You should possibly pause the video and make sure you know in advance how that will work. Which brings us to the last row, where I'll just go through it once more. Does m equal t? No. Choose the smallest of these and add 1. That gives us a 4 there. Same, t does not match m. Smallest of neighbours is 3, so we add 1, get 4. Smallest neighbour is 2, add 1, get 3. And now m does match m, so we can do a copy of this element there into that square there. I don't know what 4 is doing there. I'll get rid of that. So the final picture is the one you're seeing on the left, which should be the same as the one on the left if I did it right. And this final cell, which I'll just highlight for you, is the final cost. So we can get from them to Tim with a cost of 2. It doesn't tell us what operations were needed yet. We're going to come to that really soon now. The next example over here on the slides is a much bigger one, but the process absolutely the same. Please work through that, see if you can do it yourself, maybe on a spreadsheet, and see if you can fill out the table and get exactly that answer. Right, all that remains now is to figure out what particular sequence of operations or edit operations were needed to get them into Tim, or in this case, that horrible string into that horrible string, with the given cost at the final cell. There's actually two separate ways of going about that. One is to record, whenever you fill out a cell, how it was that you got there. So that in this particular case, I came from this cell here diagonally because the t's already matched. So I could record the predecessor cell in there as a 0, 0, or I could just record what the operation was, which was in this case an alignment operation. And then that makes the backtracking a little bit easier. But I shouldn't call it backtracking, the trace back maybe, to avoid confusions with recursive type backtracking in graphs. So this is a simple trace back through the grid. So I'm going to assume that we didn't record the predecessor information, so we're just going to have to infer it as we work our way back. There's the final cell. How did I get there? Well, I must have, since it's an M and an M, I must have come diagonally, so I must have come from that cell. And I'm going to build a sort of stack as I do this to say what happened. It was alignment. How did I get to this cell? Well, the I does not equal the E, so I must have come from the cheapest of my neighbours, one of those two. Now, I don't know which one, and it doesn't actually matter, or at least if all I'm after is any particular sequence of edit operations to get me there, it doesn't matter which one I pick. So I'm going to go with that one. That means I've gone with the substitute operation. I've substituted the E for an I. Now, how did I get here? Again, the characters don't match, so I must have come from that square there. There's no option, which was a delete operation. Whenever I come vertically, it's delete. Whenever I come from my left, it's insert. Lastly, this one here, the t's match, so I must have come from that square, so that was an alignment operation. So there's the stack of operations. I have to read this out backwards, so I have to read it out as ADSA when I went in a forward direction from there to there, which means that I aligned the T, I copied the T across, I deleted the H, I substituted E for I, and I aligned the two M's for a total cost of 2, because the alignments are 0 cost. There's a more advanced example here which you should work through. Notice there are two solutions, and there are multiple solutions in this one as well. The two solutions shown here. Look through those, make sure you understand them. That's all I have for this video. Thanks for watching. Bye.